So yesterday I looked at some polynomial theorems, today some polynomial results. So here's the first one. If we know a polynomial has k distinct zeros, so in other words, k different solutions to the polynomial, if you like, then we know that x minus a1, x minus a2, x minus must be a factor. That's just by the factor theorem. Because we know if we substitute in a1 we get 0, then x minus a1 must be a factor. Substitute in a2 and we get 0, x minus a2 must be a factor. So therefore, logically, all of those things multiplied together must be a factor of the polynomial. Alright, so let's have a look at this one. We're going to show that 1 and negative 2 are zeros, and then hence we'll go and factorise it. So polynomial 1 equals 0, hooray. Negative 2, oh yes, that equals 0 as well. U-Butte. By the way, when you're solving this sort of problem, don't just go polynomial 1 equals 0 and sort of go, well, I know it's going to equal 0 because otherwise the question wouldn't work. Show the substitution step, otherwise they're going to look at it and go, hang on. You know. Okay, so that means that x minus 1 and x minus 2 are factors, so therefore logically what they multiply together to give is a factor. So whether you do it by polynomial division or by logic, rather than writing x minus 1, x plus 2, I'm going to write the factor down as x squared plus x minus 2. And then work out the other factor. So, leading term times leading term must give x to the 4, so we have x squared. Constant times constant must give constant, so negative 2 times 5. Now, we've got several choices here. We could work out the x cubes, the x squareds, or the x's. I'm just going to go with the x's, I think. At this stage we have 5x. So it looks like it's okay, but I'm always a little bit uncomfortable with that, so I might check the x cubes as well. X squared times x, yes, x cubed, so it's looking good. It looks like the other factor is just simply x squared plus 5. So let's complete the factorisation. So we'll now get the x squared plus x minus 2 and write it as x minus 1, x plus 2. And the other factor is x squared plus 5, which of course does not factorise. Well, over the real numbers anyway. More about that later. So the next idea, if we know it's of degree n, and we have n solutions, so we've got n zeros, then we know what the polynomial is. It must be x minus a1, x minus a2, and so on. Well, at least that's if it's monic. I guess it could be a multiple of that as well, some number of times that would also have those solutions. That brings us to this idea. If you have a polynomial of degree n, you cannot have more than n solutions or n zeros. Otherwise, when you factorise it, you're going to have too many parentheses. So we now know for this polynomial, double 0 at negative 7. So 2 of the zeros are negative 7. A single 0 at 2, write down a possible polynomial. Now when they say a possible, what they're really meaning, I think, is a general sort of a polynomial that will cover every possible case. So we know x minus 2 must be a factor, and we know x plus 7 squared must be a factor. Well, what else could happen? Well, it could be multiplied by another polynomial. But that other polynomial could not have solutions 2 or negative 7. Because if it did have a solution at 2, for instance, then 2 wouldn't be a single 0, it would now become a double 0. So we know that. Could multiply it by some constant. Whether I really need to or not, because I've already said it's times a polynomial, and the constant could have been in the polynomial anyway, but it doesn't hurt. We'll put, and k, well, again, we're assuming real numbers for this. Okay, so that's a possible one. But what about if we said, no, I want it to be monic and I want it to be of degree 3. Okay, so they're the two factors. Well, that's degree 3 and that's monic, so there's nothing else it could be. In this case, there is only one possible polynomial that it could be. What about if it's monic in degree 4? So I write down the two factors that I know, which at this stage is of degree 3, so therefore I would have to multiply it by some linear function. So I'll go x minus a, but again, a could not be 2, and it could not be negative 7, or that would change the double root at negative 7 and the single root at 2. A polynomial of degree 5, well, then there's my two factors. It must be multiplied by a quadratic. Now, don't make the mistake of multiplying it by something like this. X minus A, X minus B. Yes, that's quadratic, but if you write it down like that, you're assuming that that quadratic could be factorised. It might not be. So I'm just going to say multiplied by QX, where QX is a quadratic. It's a polynomial of degree 2. Maybe it does factorise, maybe it doesn't. I don't know. And again, it will not have solutions 2 or negative 7. And once again, I suppose I could multiply that one because they didn't specify monic, so it could be times some constant as well. And here's where I now contradict myself. Right? Because I just said you can't have more than n solutions or n zeros. So what happens if it does? So if a polynomial has degree n, but it's got more than n zeros, then there's only one possibility. It must be that special polynomial that we call the zero polynomial. It's the only way it could have more solutions. Or, well, solutions is probably a bad word because there's only one solution, but more zeros. All right, so we'll just look at exercise Jolly Good Fellow.